They told us the first lights were simple, yet what if the earliest beacons were swollen with hidden engines, and their glow was a cipher for something stranger than fusion? You arrive at the threshold where ordinary stars cannot yet exist, and still the sky is littered with embers that should have taken far longer to ignite, and the question gnaws at you. What if these oversized sparks are not stars in the way we mean the word, but cocoons fed from the inside by the most elusive substance we have never seen yet everywhere in fur? A new telescope stares backward in time and finds objects that are too bright too soon, and the puzzle opens like a vault with a lock that responds to curiosity. You want an answer, and the answer whispers through equations and spectra and patient comparisons until a shape emerges that matches a bold idea older than the data itself. Long before these signals arrived on our mirrors, some scientists imagined stars that begin not with fusion, but with a quiet furnace, where dark matter particles meet and vanish into heat. Catherine Fries and collaborators described how collapsing gas in the infant cosmos could kindle on the ashless fire of dark matter annihilation and swell into vast luminous bodies. Douglas Spoliar and Paolo Gondolo helped map the criteria for that ignition, where gravity gathers and cooling falters, an invisible mass takes over the power bill of the newborn light. Such objects would be enormous and cool at the surface, yet brilliant in the infrared, and they would grow by feasting slowly without the turbulent violence that fusion imposes on a young core. Call them dark stars not because they are dim, but because their engine is hidden and their brilliance is borrowed from interactions we infer only from galaxies that move as if tugged by ghosts. The new data show candidates whose brightness and colours sit oddly for ordinary galaxies, and they hover at redshifts where the cosmic clock should not allow such luminous maturity. Cosmin Ilié and colleagues compared those colours to models and proposed that a few of these ancient embers align with the signature of supermassive dark stars, and the debate erupted like a silent flare. Spectra arrive later like slow mail from the edge of everything, and each feature is weighed like a fingerprint, while astronomers ask whether helium lines and continuum slopes favour an exotic star over a crowded nursery of little ones. The hook is here because the possibility refuses to fade, and the images keep producing objects that look too big, too young, and too efficient for the rules we trusted. Imagine a star 1 billion times brighter than the sun, yet cool enough to hide its fury in gentle colours, and imagine it swelling to 1 million solar masses by sipping from the halo that cradles it. Such a colossus would be a sanctuary where turbulence is calmed by an invisible stipend, and gas settles rather than fights, and radiation leaks out like evening from a lantern. You can almost see the light pooling on the detector as the telescope drifts and locks, and lets ancient photons finish their journey onto a wafer that will turn them into arguments. If these candidates are what the bold papers suggest, then some of the earliest bright specks are not galaxies at all, but solitary giants whose hearts hum with the statistics of annihilation. Skeptics do not fall silent because science rewards their discipline, and they remind us that a compact starburst or a nascent black hole shrouded in hot dust can mimic the same colours and confuse the most careful fits. So the story moves with restraint, and we test each candidate with deeper spectra and finer models, and the field learns to tell apart a nursery from a monolith by the faintest turn of a line. On one target, the helium feature looks persuasive, and on another, the balance of light and absence of heavy elements argue for youth beyond ordinary imagination, and we collect these hints like shells from a widening shore. Fries returns in lectures to explain the 3 conditions for dark star birth, and how capture of passing dark matter can keep the engine burning longer than the first fuel could supply alone. Illy extends the maps to show where gravitational lensing might amplify a distant candidate, just enough to nudge it over the horizon of detectability and into our lists and plots. Others, like Saiyang Zhang, forecast what a future survey could net if these objects are common, and how to triage the sky for the ones with the cleanest signatures and the least messy neighbours. Meanwhile, every frame from the deep programs is a fresh negotiation with the early universe, and we learn to be suspicious of easy triumphs, yet ready to recognise the moment a pattern hardens into evidence. Your curiosity has a sound like thin paper turning, because every parameter matters, and the mass-to-light ratio and the radius and the surface temperature must sing the same song. A dark star would be puffed up by its secret heating, and would shine with a spectrum that slopes softly rather than crackles, and if you catch the right line, you can tell the difference between a crowd and a sovereign. Think of the first billion years as a rehearsal hall where gravity auditions wild possibilities, and only some make it to the long performance, while others bow and vanish into blackness. If the candidates survive further scrutiny, then they solve a riddle about why early space looks overachieving, and they hint that black holes might begin inside these giants, when the invisible stipend finally dwindles. You can picture a finale where the quiet engine fades and the star collapses not out of fury, but out of hunger, and a seed black hole awakens at the centre and starts a different kind of growth. The camera does not care about our metaphors and keeps sending clean numbers, and we pair those numbers with models that were waiting patiently for their audition in the light. There is humility in the margins because one calibration error can masquerade as a miracle, and one stray foreground can mimic an ancient thing, and the team must prune illusions with steady hands. Still, the count of candidates inches up, and each new sighting makes the possibility less lonely, and the conjecture thins into a working hypothesis you can argue with, but not dismiss. We trace the signatures again and again and compare to synthetic spectra, and to the behaviour expected from star clusters, and we demand consistency across instruments before the story advances a step. If this is real, then the term first dark stars will pass from a cautious question to a provisional headline, and the earliest chapter of Starlight will tilt toward an engine made of absence. You want to know whether the claim stands tomorrow, and the answer is that the universe is patient, and so must we be as more spectra arrive and more candidates are sifted. For now, the best you can do is follow the evidence with the same hunger as those photons that crossed a young darkness to reach a mirror and whisper maybe into the ear of a waiting century. Hold that maybe as the hook and the promise, because the next frame could carry the line that tips the scales and turns speculation into a provisional map of how light began. And when that moment lands, you will recognise it not by the noise, but by the quiet fit of theory and data, and the feeling that something complicated just became simple enough to keep. Until then, keep watching the story that started with an audacious idea and found companions in the deep fields where time runs thin and the earliest lanterns still glow. We return to the question with quieter breath, because the early universe does not shout, and the clearest answers arrive like snowflakes that refuse to melt when the lamp of skepticism is held close. The James Webb Space Telescope keeps handing over objects whose light curves and colours sit just off the paths traced by ordinary infant galaxies, and each offset is a whisper that the engine beneath could be unusual. Volker Brom reminds us that first light is a fragile phase where cooling, collapse and feedback braid into a single performance, so any alternative engine must match the rhythm of those braids without snapping them. Avi Loeb urges patience with audacity because the cosmos sometimes wears a mask made of selection effects and gravitational lensing, so we test the mask by mapping magnification and checking whether brightness owes more to the lens than to the lamp. Consider a candidate framed by a cluster whose gravity acts like a glass blower, shaping the path of ancient photons, and imagine how a small source might masquerade as a grand one, unless the lens model is tuned like a fine instrument. Priyamvada Natarajan has shown how the architecture of dark matter halos sculpts both galaxies and black holes, so a star powered by dark interactions would be a cousin born in the same house but fed at a different table. If such a star swells to 1 million suns in mass, its surface stays cool by stellar standards, while its interior basks in the heat of annihilations. Its spectrum glows softly in the infrared like banked coals under ash. This softness matters because crowded star clusters scream in ultraviolet lines, and hot dust around a growing black hole mutters in mid-infrared humps, while the proposed dark star croons a steadier song that leaks through a wide window. Daniel Whalen sketches simulations where gas streams inward without severe turbulence when that quiet heating is present, and the radius balloons so dramatically that gravity holds without the shock of early fusion tantrums. Rafaela Schneider places these giants on the timeline beside the first heavy element factories, reminding us that if the early spectrum lacks metals, then we are indeed seeing a stage set before conventional furnaces light. Marta Voluntari threads the needle to the later universe by asking whether a dark star's quiet end could seed a black hole that grows into the hulking engines we see anchoring bright quasars by redshift 7. If the path from invisible heating to central collapse is true, then part of the quasar mystery softens because we no longer require a dozen miracles of merger and accretion in a time span that barely allows one. You watch the spectrum arrive from another deep pointing, and the faint helium line steps forward without the messy companions, that massive star clusters usually drag along, are the fitlands like a key in a long-locked door. The team cross-checks calibration lamps, flat fields, and background subtraction because the easiest miracle to believe is a reduction error that clung like dust to the edge of the pipeline. Meanwhile, theorists refine opacities and annihilation rates, folding in uncertainties for the cross-section of dark matter particles, because an engine is only as honest as the numbers that feed it. Some critics point at superstar clusters wrapped in hot gas that can mimic a smooth glow, so observers schedule longer exposures to hunt for the grainy structure those clusters cannot hide forever. Others raise the banner of nascent black holes shrouded by inflowing streams, and they ask for the telltale high-energy breath that even thick veils cannot fully smother if the furnace is truly compact. The James Webb Space Telescope instruments are tuned to listen for that breath in the redder registers where ancient expansion has stretched each photon, and a missing growl strengthens the case for an extended source. Cosmic variance enters like weather and reminds us that a handful of fields cannot speak for the whole sky, so surveys widen their nets and borrow time from every schedule willing to bend. John Wise models how the earliest halos filter ultraviolet light from the first conventional stars, and his grids become a ruler to measure whether the candidates live inside neighbourhoods too calm for furious nurseries. Pascal Ursh and Brant Robertson press photometry against spectroscopy, asking whether the broad colours truly predict the sharp lines, because consistency across methods is where fragile ideas harden into weatherproof claims. Richard Ellis, steady on the bridge between observation and interpretation, cautions that interloper galaxies at lower redshift can masquerade as ancients if a dusty veil tilts the colours, so every candidate must pass a gauntlet of alternative fits. Tiziana Di Matteo reminds us that rapid black hole growth can sometimes outpace our instincts, which keeps the shrouded accretion scenario alive as a competitor until the faintest slopes of the continuum are pinned down. Xiaohui Fan carries the ledger of known early quasars and asks whether the number of seeds implied by the candidates comfortably accounts for the giants we count by 1 billion years, or if a second route must still run in parallel. The narrative breathes with these cross-examinations. You keep the hook alive by promising not fireworks, but the soft satisfaction that comes when disparate measurements finally tell the same simple story. Now imagine the life of a dark star measured not in violent pulses, but in long seasons where annihilation, heating, and gentle accretion trade places as dominant forces, lengthening youth until the surrounding reservoir thins. When the stipend wanes, the core compacts, temperatures spike to the threshold where fusion awakens like an old hymn remembered, and the object either stabilizes briefly or cascades toward catastrophic collapse. If collapse wins, a black hole appears with a mass already far above the seeds left by ordinary massive stars, and the infant galaxy now holds a kernel with momentum, enough to sculpt its future. Feedback from that new hole may blow a bubble or heat the neighbourhood, but the earliest era is a place where even feedback learns its manners slowly, so the imprint could be subtle and widespread rather than brash. Back on the detector, the light is translated into numbers and then into plots, where each point carries error bars like quiet honesty. The students learn that patience is a scientific instrument too. You do not need a miracle for this story to work, only a set of consistent measurements, and a theory that resists being cornered by its own predictions, which is rarer than it sounds. Consider how the absence of strong metal lines at these epochs dovetails with the notion that heavy element forges had not yet fired broadly, leaving room for objects whose surfaces keep a cool, metal-poor signature. Then consider how a core density profile of dark matter inside a halo could extend the heating season, while a cuspy profile might concentrate power and shorten the pre-fusion era. A difference observers may glimpse in subtle slopes. Next season the telescope will revisit several fields as parallax and proper motion checks to rule out nearer mimics, because even a perfect spectrum means less if the source sneaks closer than claimed. By then, laboratory teams will have narrowed viable ranges for dark matter interactions, and though no direct detection has yet rung the bell, even a null result chisels the parameter space into a sharper alcove. Astronomers will also ask radio arrays to listen for any faint breath from surrounding gas, since a quiet radio environment favours an extended stellar body over a compact accreting monster. Gravitational microlensing events across the field may add another test, because a truly large stellar radius responds differently to a passing caustic than a tight core bound around a black hole. In parallel, supercomputer experiments will stitch together hydrodynamics and particle annihilation heating with finer meshes, and the emerging movies will teach us which observable details survive the harsh cut of reality. We will rank candidates by the clarity of their neighbourhoods, favouring those without clutter from messy companions, since a sovereign object in a clean frame yields conclusions that travel well. If 2 or 3 gold standard sources pass every check, the field will adopt a careful new term of art that admits uncertainty while marking discovery, and students will learn it the way sailors learn currents. If none survive, the lesson will be just as valuable, because it will pour cold water on a tempting path and redirect attention to the stubborn power of ordinary processes in extraordinary circumstances. Either outcome moves the story forward, yet the present tilt of evidence keeps your attention tuned to the possibility that the first lanterns were inflated by invisible fuel before they burned on familiar fire. So you stay for the next frame, which will not be a thunderclap but a new stitch in a careful fabric, sewing together colour, line, radius, and neighbourhood into a garment the early universe can plausibly wear. The promise to the viewer is simple and honest, that by the end of this journey you will either hold a new origin story for the brightest seeds or a sharpened map of how ordinary stars learn to act heroic so soon. Keep your questions sharp and your doubts sharper, because the cosmos rewards that posture, and let the ancient light speak at its own pace as we learn to hear engines we cannot see. When the credits roll on this chapter, you will know why some scientists suspected dark stars, how the James Webb Space Telescope tested the suspicion, and what remains before suspicion graduates to knowledge. For now, the hook stays, not as bait but as truth in transit, and the next observations will decide whether the first dark stars are a rumour from the edge or a cornerstone for the dawn of structure. The first clue is colour that leans red, not because the source is cold, but because the universe has stretched every photon across eons, and the James Webb Space Telescope reads those stretched colours like a diary written in soft ink. Photometry shows brightness in filters that gather long wavelengths, where the afterglow of expansion leaves its signature, and the shapes of those brightness steps line up with models where a swollen stellar surface hums instead of crackles. Spectroscopy follows with careful teeth that bite the spectrum into thin slices, and in those slices we hunt for helium hints, or the absence of heavy element noise that would betray a bustling factory of ordinary massive stars. The near-infrared camera delivers images whose clarity lets us separate a smooth lamp from a swarm of smaller sparks, and the smoothness becomes its own kind of evidence when the profile refuses to break into grain. The near-infrared spectrograph listens for lines riding atop a gentle continuum, and the quiet slope suggests an extended photosphere rather than a compact engine buried in dust that would spit harsher features. The mid-infrared instrument adds a test by looking deeper into wavelengths where warm dust would glow if a hidden black hole were raging nearby, and the restraint of that band supports the picture of a broad and cooler stellar skin. Candidates sit at distances that translate to less than 1 billion years after the beginning, and their luminosity would be a tall order for normal galaxies assembled from scratch in such brief time. A dark matter engine can relieve that pressure, because annihilation heating supplies power without the immediate need for core fusion, allowing a body to inflate to vast radius while staying relatively cool at the surface. The gas falls inward along filaments that thread the first halos, and instead of igniting violently, it settles under the steady stipend of invisible interactions that turn mass into heat with fanatical discretion. Surface temperatures land in a range that favours infrared glow over ultraviolet scream, which is why these objects look like lanterns under fog rather than lightning bolts in clear air. Because the radius is enormous, the gravitational pull at the surface is gentle compared to a compact star, so winds escape differently, and the observational fingerprints drift away from patterns recorded in familiar stellar families. Light profiles measured across the detector confirm the lack of sharp cusps that would betray a point source conspired by lensing, though gravitational lensing remains a constant risk that teams model carefully before claims grow teeth. Time delays across multiple observations test whether the brightness is stable in the slow way an extended object prefers, rather than jittering like a hungry compact nucleus gulping gas in fits. Noise is the enemy of wonder and calibration is the sword, so flat fields, background subtraction, and wavelength solutions are cross-checked until the residuals fall below the level where fantasies are born. The James Webb Space Telescope was built for this patience, with optics that live in deep cold and instruments that speak softly in the language of electrons, so ancient light can land without thermal chatter. To move from candidate to confidence, the field needs multiple independent objects showing the same serenely inflated character, distributed across different lines of sight so that chance and coincidence have nowhere left to hide. If even a few meet that bar, the early growth of black holes no longer requires frantic merger trees, because quiet collapse of a depleted dark star can plant a seed that begins life already large. Such a path eases the timeline for bright quasars by redshift 7, not by magic, but by shaving the impossible into the merely demanding, which is the hallmark of a good physical story. Skeptical alternatives survive each round because a compact starburst hidden in dusty gas can imitate the colour of a giant, and a small active nucleus can fake smoothness if lensing smears its sparks, so every case must pass multiple gates. Radio silence in the neighbourhoods of the best objects helps, since compact accretion often breathes in radio, while an extended photosphere whispers mostly in infrared and leaves the radio dial calm. Another clue lies in the absence of strong metal lines, because a society of older stars would have salted its environment with heavy elements by supernovae, and these spectra look more like a kitchen still waiting for its first fire. Brightness temperature estimates, derived from surface flux and radius fits, point to cooler skins than expected for massive fusion engines, which again supports the picture of size without the usual heat. The James Webb Space Telescope point spread function is stable enough that deviations from a point source can be trusted when the images are deep and the field is uncrowded, converting shapes into arguments rather than illusions. When colours across filters map a smooth slope with gentle curvature, models of extended atmospheres heated from within by dark matter, interactions reproduce the slope gracefully, while compact dusty nuclei require more contortions. A further test comes from searching for flicker across months, because a swollen body powered by steady annihilation should vary slowly, while a small accretion disk can jitter with supply issues and local storms. The telescopes on the ground join by measuring complementary wavelengths with adaptive optics, checking that no hidden companions sit close enough to counterfeit a single giant with their blended light. If the dark star interpretation holds, early galaxies would inherit central masses sooner, changing the feedback story and perhaps softening the first bursts of rionization into a patchwork that begins with pockets rather than a sweeping front. Rionization history then becomes a ledger sensitive to how many of these gentle engines lived, and for how long, because their softer spectra contribute fewer ionizing photons than the same luminosity from hot fusion furnaces. The balance between annihilation heating and baryonic accretion decides the lifetime, with capture of dark matter from the surrounding halo prolonging the fuel supply, like rain feeding a quiet reservoir. Eventually the reservoir falls below a threshold, the radius contracts, core temperatures rise to fusion criteria, or collapse proceeds to a black hole direct, with observational signatures that depend on how sharply the transition occurs. The James Webb Space Telescope cannot watch a single object evolve across cosmic centuries, but it can sample many objects at different apparent ages, turning the sky into a time series written across distance. Catalogues now include shortlists ranked by cleanliness of environment, depth of spectra, and agreement between imaging size estimates and spectral energy distributions, because ranking evidence is how a community keeps its balance. In the best cases, the half-light radius exceeds what a lensed compact source could mimic, without leaving shear signatures nearby, adding geometric weight to the claim of true extension. Targets behind known lensing clusters are modelled with multiple mass maps to bracket uncertainties, since an error in the glass can inflate or deflate hope as efficiently as a mistaken exposure time. Parallel observations in the mid-infrared band confirm that any dust contribution is modest, because a large mid-infrared hump would argue for heated grains near a compact core rather than a broad stellar surface. Planned follow-up seeks faint recombination lines that would appear if a thin shell of ionized gas surrounds a cool photosphere, a subtle halo that would be unwelcome around a bare accretion engine. A final sanity check compares number counts against theoretical formation rates, asking whether the sky holds too many or too few candidates for a model that seeds only rare halos with sufficient dark matter density. The viewer deserves clarity, so the story remains careful that the James Webb Space Telescope has revealed sources whose properties match expectations for stars powered by dark matter, while alternate explanations continue to be tested with vigour. What makes this exciting is not a headline, but a convergence of signs, from colour to size to spectral restraint, all leaning toward a picture where the first lights were gentler giants with hidden fires. Each new deep field is a fresh roll of the dice weighted by physics, and with every clean detection, the probability that these engines exist moves from romance toward responsibility. The hook that keeps you listening is simple, that we may be learning how the first gravitational wells learned to glow, not by hurry, but by patience, turning invisible matter into warmth that sculpted the path for everything that followed. Stay with the data as it grows thicker, because the distance between maybe and likely is crossed by small bridges, the kind built from repeated measurements, independent analyses, the stubborn refusal to hurry the truth. We pivot from curiosity to measurement because the promise lives or dies on whether light, size and time all point to the same hidden engine as the James Webb Space Telescope pushes deeper into fields selected for clean skies and minimal gravitational clutter. We now focus on how an extended photosphere changes the way light escapes, because a broad surface with lower gravity per square meter lets photons random walk for longer paths, and the resulting spectrum smooths into a gentle curve that matches what the James Webb Space Telescope records. A cool surface temperature with a very large radius means the total luminosity can still be enormous, since area multiplies the modest flux, so brightness does not require a scorching skin if the star is puffed up by invisible heating. Dark matter annihilation in the core supplies this gentle pressure, preventing immediate collapse to the fusion threshold, so gas settles into equilibrium at lower central temperatures, while still radiating abundantly from a photosphere that spans light years on the largest models. The James Webb Space Telescope turns these ideas into tests by collecting light across carefully chosen filters, building a spectral energy distribution that can be compared with model atmospheres that incorporate internal heating from particle interactions rather than nuclear burning. When the best-fitting temperature lands below that of typical massive fusion stars at similar luminosity, while the size implied by the shape on the detector suggests a resolved or marginally resolved source, the case for a swollen object strengthens. The colour break associated with neutral hydrogen tells us the distance, because absorption in the far ultraviolet is shifted into the near-infrared by cosmic expansion, so the Lyman break appears where the universe places it for the measured redshift. Foreground imposters are rejected when their colours fail to mimic that break across multiple filters, with simulated interlopers injected into the images to verify that our selection would not be fooled by dusty nearby galaxies. The shape of each candidate is checked against the telescope point spread function, a known fingerprint that can be subtracted, and when residual extension remains across orientations and roll angles, the extension belongs to the source rather than the optics. Light curves measured over months show steadiness consistent with a large radiating body, since accretion disks around compact engines often flicker as supply varies, while volume-powered stars should change very slowly if the reservoir is stable. Radio observations add a quiet line of evidence, because strong compact accretion commonly yields radio emission from jets or winds. Yet the neighbourhoods of the most persuasive candidates remain calm at radio wavelengths. Mid-infrared checks also help, since hot dust would glow strongly near a hidden compact core, but the mid-infrared signature stays restrained in the cleanest cases, which argues for a broad photosphere rather than dust heated near an active nucleus. Spectroscopy hunts for helium features and the absence of heavy element lines, because a population rich in older stars should have salted the gas with metals, while a very early object with gentle internal heating would remain metal poor. Neutral gas along the line of sight can imprint damping wings that complicate the profile near the break, so teams model intergalactic absorption carefully to make sure distance and intrinsic slope are not being conflated. Gravitational lensing is modelled with multiple mass maps for any foreground cluster, because even a small error in the magnification can inflate the inferred size and luminosity. So claims rest only on cases with consistent magnification across reconstructions. If magnification is modest or absent and the source is still bright, the demanding arithmetic of the early timeline loosens, since we no longer need extreme star formation in a tiny volume to reach the observed luminosity. Theoretical expectations say these bodies should present cooler colour temperatures while remaining very bright, a combination that the James Webb Space Telescope can diagnose because its instruments span a wide wavelength window with stable sensitivity. Noise control is essential, so flat fields are verified, background subtraction is repeated with different apertures, and spectra are extracted with independent pipelines to ensure that a gentle slope is not the ghost of processing. When multiple reduction methods agree on the same continuum, confidence grows that we are reading the sky rather than the software, turning faint counts into physical claims that can be reproduced by other teams. Number counts are then compared to formation models that predict how many halos possess the central conditions for strong annihilation heating, with uncertainties from particle physics carried through as ranges rather than single values. The implication for early black hole growth follows naturally, because a giant star depleted of its invisible fuel can tip into collapse with a mass far above the remnants of ordinary massive stars, planting a seed already primed for rapid growth. This path reduces the urgency for frequent mergers in the young universe, since fewer but heavier seeds can reach the observed masses of early quasars within the available time without demanding a chain of unlikely coincidences. The influence on reionization is nuanced, because cool extended photospheres produce fewer ionizing photons per unit luminosity than hot compact clusters, so even bright populations of dark matter-powered stars would likely contribute more to warmth and structure than to ionizing the entire sky. A final observational signature could be a very faint nebular halo from gas warmed by the broad stellar surface, weaker than the loud regions around compact engines, which future deep exposures may detect as a soft rim. Selection effects remain a caution, since fields chosen for lensing or for low background may bias the sample toward environments that amplify certain sources, so survey strategies include blank fields to measure the unbiased sky. The James Webb Space Telescope excels at this balance by scheduling programs that mix cluster lenses with unlensed depths, letting the community compare the frequency of candidates across very different observing geometries. Independent checks from large ground-based telescopes with adaptive optics will refine shapes at shorter wavelengths, testing whether the extension persists and whether any hidden companions lurk within a fraction of an arcsecond. Parallel analysis looks for subtle asymmetries that might betray a blend of sources or a slight shear from lensing, because a true single giant should present a symmetric core with smooth wings after the telescope fingerprint is removed. As the list of vetted candidates grows, modelers refine the internal structure by adding convection, radiation transport, and capture of passing dark matter from the halo, exploring how each ingredient stretches or shortens the luminous youth. Capture matters because fresh invisible particles wandering through the star can be trapped by gravity and interactions, replenishing the annihilation fuel and keeping the photosphere inflated longer than the initial reservoir alone would allow. The transition out of the inflated phase may proceed quietly or catastrophically, depending on the balance between cooling, capture, and collapse, with observational outcomes ranging from a dimming giant to a direct plunge that seeds a black hole. We cannot watch a single object age across billions of years, but we can build a population across distances that represent different times, reading evolution statistically by comparing many sources that occupy neighbouring epochs. The promise of confirmation rests on agreement across instruments, across teams, and across fields, since a true class of objects will leave a consistent fingerprint no matter who observes or which patch of sky they choose. In this light, the James Webb Space Telescope has done more than supply pretty pictures. It has delivered a disciplined way to interrogate the earlier structures with sensitivity and resolution that turn philosophical questions into measurable claims. Every new candidate that passes the gates narrows the space left for ordinary explanations, not by drama, but by arithmetic, by colours that stay too cool, by profiles that stay too broad, by mid-infrared restraint that refuses to flare. If future observations reveal a small set of gold standard examples with clean spectra, minimal lensing, steady light curves, and consistent sizes, the cautious conclusion will be that the universe once hosted luminous bodies whose power came from dark matter. Such a conclusion would ripple into how we think about the first galaxies, because a quiet internal heater changes how gas moves, how feedback behaves, and how early structures avoided tearing themselves apart before they could organize. Even a negative outcome, where all candidates become ordinary with better data, would still be progress, because it would calibrate our reading of the early universe and strengthen the case for rapid assembly by familiar processes. Either way, the path forward is the same: to keep measuring with care, to keep separating instrument fingerprints from real extension, to keep testing lens models, to keep demanding agreement before naming what we see. The hook remains honest, that we might be witnessing light from stars powered by dark matter, that shone before fusion took over the cosmic stage, their radiance a patient expenditure of energy from the most elusive component of the cosmos. Stay with the evidence as the James Webb Space Telescope deepens its view, because the union of colour, size, calm variability, and mid-infrared restraint is either the first clear signature of dark matter-powered stars or the final lesson that nature chose another route. The next test leans on how a giant body cools across its vast surface, because a photosphere spread over an enormous radius radiates with measured calm, and the James Webb Space Telescope sees that calm as a slow slope from shorter, near-infrared bands to longer ones that refuse to flare like dusty compact engines. Brightness measured across repeated visits remains steady within gentle limits, which fits the picture of a volume-powered star that sips fuel from invisible interactions rather than gulping gas. So the light curve reads like a heartbeat at rest instead of a pulse, hammered by storms in a thin accretion disk. Images sharpen the claim because the point spread fingerprint can be removed with confidence, and the remaining glow keeps a soft profile that persists across roll angles, which means the extension belongs to the source and not to the telescope or to quirks of the detector that would rotate with the optics. Colour selection fences out imposters by demanding a hard step where the universe draws the Lyman break, so any nearby dusty galaxy that tries to mimic the tone fails the multi-filter test, while true distant sources keep the correct silence blueward of the break and speak again in the redder bands. Spectra support the distance with a continuum that tilts with expansion, and hints of helium rather than a choir of heavy element lines, which would announce prior generations of normal stars, so the simplicity of the spectrum becomes a witness for youth rather than a boast for chemical maturity. Mid-infrared restraint closes another door on compact engines, because heated grains near a ravenous nucleus would glow like a banked furnace, yet the best candidates show quiet mid-infrared hum that fits a broad, cool surface, turning dust into a background singer instead of the lead voice. Gravitational lensing remains a careful companion rather than a loophole, since foreground mass can magnify or stretch, but when independent models agree that the magnification is small or moderate, the remaining luminosity and size must be owned by the source itself with no generous gift from cosmic glass. Number counts meet theory on level ground by asking how many halos should carry the densities needed for strong annihilation heating, and the sky does not overflow nor run dry, which leaves room for a rare population that matters without breaking the arithmetic of early structure. The internal engine works like a quiet stipend paid in heat, because dark matter particles meet in the densest regions and vanish into energy that balances weight, so the core stays swollen, the surface stays cool, and the lifetime of the inflation stretches while nearby gas keeps settling instead of sparking fierce turbulence. When that stipend fades by depletion or by a fall in capture rate, the gentle balance fails, the core contracts, temperatures rise to nuclear thresholds, or gravity outruns pressure entirely, so the object can either ignite fusion for a brief late chapter or collapse directly into a black hole seed. This pathway smooths the origin of early massive black holes by starting heavy, rather than racing through endless mergers, so the bright quasars that appear by 1 billion years after the beginning no longer require an unlikely treadmill of uninterrupted growth but can grow from seeds already tall. Reionization feels the difference because a cool extended photosphere does not flood space with the hardest photons, so even bright populations of these stars would light neighborhoods gently, while normal hot clusters carry more of the burden for carving ionized bubbles across the young cosmic fog. The James Webb Space Telescope strengthens each step by cross-checking instruments, because the near-infrared camera draws shapes, the near-infrared spectrograph sketches lines and slopes, and the mid-infrared instrument vetoes dust-heavy alternatives, which means agreement is earned across different lanes of the spectrum. Calibration holds the line with flat fields verified against lamp standards, background measured in concentric apertures, and wavelength solutions checked on skylines where available. So the signatures we trust survive not only imagination but also the ordinary errors that hunt for a place to hide in faint data. Foreground stars and brown dwarfs are dismissed with size and colour tests, since a nearby point source cannot fake a resolved profile at the same time it pretends to be ancient, so the combination of extension and distant colour is a lock that local actors rarely pick. Radio silence helps again, because compact engines often breathe radio winds or jets even when dust hides their faces, yet the neighbourhoods around the most persuasive sources remain quiet, letting the infrared voice carry the song without a radio echo to betray a hidden nucleus. The gentle continuum also teaches us about the atmosphere of a swollen star, because lower gravity at the surface reduces pressure broadening and line strengths, leaving subtle features that match the expectation for a cool, metal-poor skin that has not yet been salted by explosive ancestry. Simulations of radiative transport through such an inflated envelope predict a color temperature that lags the bolometric power, so the source can shine like a beacon while wearing the colors of a mild ember, which is the paradox that first drew attention to these candidates in the deep fields. Survey strategy becomes part of the science, because fields behind clusters deliver magnified reach, while blank fields measure the honest baseline, and the agreement of candidate properties across both styles of viewing argues that we are not being fooled solely by the choice of stage. Parallel checks on shapes use adaptive optics from the ground to ensure that no hidden companion blends light into false extension, and when independent facilities see the same smoothness, the case for a single giant grows sturdier than a claim pinned to a single instrument. Variability on seasonal timescales continues to favour quiet engines, since accretion flows boisterously adjust to supply, while annihilation-powered interiors cruise at a pace set by density and capture, producing light curves that change only slowly with no edgy flicker to betray a small hot core. A cautious forecast follows from the arithmetic that even a modest population of these stars could seed enough early black holes to explain bright quasars without invoking extreme duty cycles, while still leaving room for other channels to contribute in crowded or turbulent neighbourhoods. The same forecast says ionization remains a team effort, where hot clusters shoulder ionizing work and dark matter, powered stars shape the thermal background, and the slow build-up of central mass, which is how a gentle giant can matter greatly without shouting. Practical limits also appear, because the James Webb Space Telescope cannot chase every candidate with deep spectroscopy, so photometric standards must carry more weight, which is why teams build careful training sets from the cleanest examples to guide selection without drifting into wishful thinking. Future efforts will push to detect whisper-thin nebula halos around the coolest giants, where recombination in nearby gas paints a dim rim that would be out of character for compact engines, but natural for a broad star that bathes its surroundings with soft light. Expect also a closer look at the neighbourhoods, because if these objects prefer the centres of young halos, we should see patterns in local overdensities and weak lensing shear, subtle fingerprints that speak to where invisible matter piles up most helpfully for the hidden engine. Each time a candidate survives another gate, the narrative tightens that the James Webb Space Telescope has revealed sources whose best explanation is a star powered by dark matter for a long early season, before gravity eventually insists on a new arrangement. The hook for the viewer is not a twist, but a dawning sense that the first lights were not rushed miracles, but patient lanterns, swollen by fuel we cannot see yet can weigh by its effects, which is the kind of wonder that grows stronger under scrutiny. We stay with cautious clarity, stating that alternative pictures remain possible for a subset of sources, yet the set of shared traits keeps leaning toward extended photospheres, cool colours, steady time behaviour, and mid-infrared restraint that together sketch the silhouette of a dark matter-powered star. The James Webb Space Telescope keeps doing what it was made to do, holding ancient photons with cold mirrors and quiet electronics, letting signals as faint as dew survive the voyage across time so we can weigh them against models that were once only equations and hope. In this balance of patience and precision, the sky yields its most reserved secrets, and the possibility that the earliest bright beacons were swollen by invisible heating becomes not just plausible, but testable, which is the highest compliment science can pay to ideas that began as whispers. So we keep measuring, we keep cross-checking shapes, colours, lines, and radio silence. We keep building samples that span fields with and without lensing, until the weight of consistent evidence says quietly that the first stars powered by dark matter were real, and their light has finally reached us. We return to the light itself because the safest ending is written by photons that keep their promises across billions of years. And the James Webb Space Telescope reads those promises with a patience that turns suspicion into structure without rushing the conclusion. The most persuasive candidates share 4 habits at once: cool colour temperatures for their brightness, smooth extension that resists shrinking to a point, mid-infrared restraint that refuses a dust-heavy chorus, and calm light curves that prefer a steady breath over jitter. Colour tells distance through the Lyman break, so the sources sit in a time when the universe was less than 1 billion years old, which means their luminosity must be earned with physics that can work quickly without demanding crowded factories of short-lived massive stars. Size turns into evidence when the point spread fingerprint is removed and a soft halo remains across roll angles, because a truly compact engine smeared by lensing would still leave sharp clues that bend with the telescope rather than stand with the sky. The spectrum behaves like a quiet hillside rather than a jagged skyline, a gentle continuum with modest features where helium may whisper and heavy element lines do not shout, which matches a broad photosphere with metal-poor gas warmed from within. Mid-infrared silence matters because hot dust loves to sing loudly near compact accretion, yet in the cleanest cases that song is faint, leaving the broad, cool surface as the lead voice that best explains the measured energy distribution. Radio checks keep the picture honest, since active nuclei often exhale through jets and winds, but the skies around the strongest candidates stay quiet, aligning with an extended star that wastes little energy on focused outbursts. Gravitational lens models are brought to the front of the table and compared in teams, because magnification can borrow brightness that does not belong to the source. Yet for the best cases, the consensus magnification is small to moderate, and the remaining light must be owned by the object. When brightness is folded through temperature and radius, the arithmetic favours a very large area radiating gently rather than a small furnace blazing cruelly, a signature that sits exactly where annihilation heating would hold a star swollen for a long youthful season. Inside that swollen body, dark matter interactions deposit heat where gravity would otherwise force a quick dive to fusion thresholds, so equilibrium is drawn not by a sudden match strike, but by a steady stipend that balances weight with warmth. This balance changes how gas flows through the first halos, turning chaos into order as inflow settles rather than shatters, which lets the star grow in calm layers and present a spectrum that glows softly instead of snapping with violent lines. Light curves measured over months keep a slow beat that matches volume-powered engines, because annihilation rates in dense cores drift only with capture and structural change, while accretion disks around compact nuclei tend to flicker with hunger. Number counts meet formation models without strain, suggesting a rare population that still matters, enough to seed early central masses yet not so many that the sky would drown in them, which is what a reasonable cosmos looks like. If even a small fraction of these objects end their inflation by collapse, the resulting seeds begin life already heavy, which lowers the demand for frantic mergers and allows bright quasars to appear on schedule by the first billion years. Ionization adjusts around them because cool extended photospheres supply fewer hard photons per unit light, so their role is to warm and organize while conventional hot clusters carve the cleanest ionized bubbles in the fog. The James Webb Space Telescope earns confidence by redundancy, with images from the near-infrared camera, spectra from the near-infrared spectrograph, and mid-infrared checks from the mid-infrared instrument agreeing on the same quiet portrait in independent frames. Pipelines are tested with flat fields, background annually, alternative extraction windows, and independent teams, because the difference between a gentle slope and an artifact is a handful of counts, which is why the community treats every count like a witness under oath. Contaminants are challenged with injections of simulated imposters that try to sneak past colour selection, but the survivors of the gauntlet still carry the right brake position, the right smooth profile, and the right mid-infrared restraint to keep the stronger claim alive. Ground-based telescopes with adaptive optics confirm the lack of close companions that could blend into a false giant, while weak lensing sheer maps of the neighbourhoods look ordinary, arguing that we are not being tricked by a special alignment. The internal physics remains simple in spirit even if complex in detail, with dark matter supply through capture extending the luminous youth, and with the endgame set by whether the reservoir dwindles slowly into fusion or collapses directly into a black hole. Spectral energy distributions that include the longest available wavelengths continue to prefer cool color temperatures for large luminosities, a combination that ordinary compact stars would struggle to sustain without thick dust that the data do not support. Future work will search for faint recombination halos around the most extended sources, a subtle scarf of ionized gas that would suit a broad photosphere bathing its environment, yet would be unusual around a naked compact nucleus. Parallel fields without lensing will build an honest census, while cluster fields will push farther down the luminosity function to see whether smaller versions exist, because a class becomes real when it shows a family of sizes rather than a single celebrity. The viewer's question is simple. Did the telescope truly find stars powered by dark matter? And the careful answer is that it found candidates whose full set of properties align with that engine more naturally than with the usual suspects, while alternative pictures are being tested with equal vigour. As the evidence converges, the story of early structure becomes less frantic, because a gentle heater can organise gas efficiently, seed central mass gracefully, and leave behind observables that survive expansion like pressed leaves in a book of time. Even the null paths have taught us something, because every rejected candidate improves the selection rules, sharpens the lens models, tightens the calibration, and makes the surviving cases cleaner than they were a season earlier. We therefore walk toward closure by insisting on agreement across colour, size, spectra, lensing, mid-infrared quiet, radio silence, and stable time behaviour, because only a chorus can certify what a solo might counterfeit. If the chorus holds, we gain more than a label. We gain a mechanism for the first light that complements fusion, a way to turn invisible mass into warmth that shaped the stage where ordinary stars would later perform. If the chorus breaks, we gain clarity about the limits of look-alike phenomena, and we refine the story of rapid assembly using only familiar tools, which is still a victory for an instrument built to replace speculation with measurement. Either way, the James Webb Space Telescope has proven that the dawn can be read in detail, that spectra can be gathered where darkness once looked mute, and that patience is the proper cost of hearing the earliest voices. For the strongest remaining cases, the half-light radius remains large after every correction, the continuum remains gentle after every pipeline, the mid-infrared stays modest after every integration, and the colours sit exactly where expansion says they should. These are the signatures that earn the phrase dark matter-powered star as a working interpretation rather than a wish, pending deeper spectroscopy that can find the faintest features and lock the distance with even tighter certainty. In that spirit, we hold the hook with an honest promise that the next season of data will not aim for spectacle but for agreement, because agreement is the form that truth takes when many instruments look at the same shy thing. So keep the question alive while we prepare the final checks, because a universe that allowed its first lanterns to shine on an invisible fuel would be a universe that turned absence into power, a transformation as elegant as any law we teach. If that transformation is confirmed, the path from early halos to early black holes will read like a single sentence, a swell sustained by quiet heating that ends in a collapse heavy enough to anchor the brilliant beacons we see later. If instead the candidates resolve into compact engines wrapped in dust or blends of smaller sources helped by glass, the map improves anyway, because we will know exactly how nature fakes the signature and how to avoid the trap next time. This is the value of a telescope that measures rather than merely looks. It takes a rumour from the horizon of time and demands that the rumour survive colour tests, size tests, line tests, and silence tests before it earns a place in the story. We round the bend toward resolution with gratitude for precision, because it is precision that turns metaphors into models, models into plots, plots into shared beliefs, and shared beliefs into foundations that future questions can stand on. Let the last word of this segment be patience, since the light we weigh tonight left before our planet knew its first sunrise, which means the only respectful way to greet it is with care, with skepticism, and with a readiness to be surprised by how quietly truth can speak. We hold the frame steady because closure depends on discipline, and the James Webb Space Telescope gives us that discipline by repeating measurements until shape, colour and time behaviour line up without begging for special pleading. The candidates that stay in the circle after every cut share the same quiet signature, cool for their radiance, broad in their light profile, unexcited in the mid-infrared, and nearly motionless in brightness across the months we have watched. Distance is anchored by the Lyman break that falls exactly where expansion predicts, so we are not mistaking a nearby ember for an ancient lantern, we are reading the correct page in the diary of the sky. Extension survives subtraction of the point spread fingerprint, which means the glow is truly spread across space, and not the smear of a point source disguised by optical quirks or an unkind angle. Spectra bend like a soft hillside rather than a saw, which fits a wide photosphere that is metal poor and calm, warmed from within by interactions that do not require the sudden violence of early core ignition. Mid-infrared silence is a veto against dust-fed compact engines, because a hungry nucleus loves to heat grains into loud choruses, yet the best cases stay modest in that band and leave the broad surface to do the speaking. Radio checks add another veto, since compact accretion often breathes through jets or winds, but the neighbourhoods of the strongest candidates remain quiet, a match to a wide star that spends power as light rather than as directed outflow. Gravitational lensing models are consulted like careful accountants, and where magnification is small to moderate, the brightness must be owned by the source, while shape tests reject the extreme shears that would betray a masquerade. Arithmetic turns kindness into evidence, because a cool surface at enormous radius can still pour out light through area, so luminosity does not demand a blistering temperature if the photosphere is huge. Inside that width, the hidden heater pays a steady stipend of warmth, lifting the core against collapse, and the star remains puffed until the reservoir of captured invisible particles thins below the level needed to balance gravity. When that balance fails, the object either glides into late ignition or yields to gravity and plants a central mass that begins as a heavy seed, a path that softens the schedule for the earliest bright quasars. Reionization reads this difference as a change in tone rather than volume, because these cool giants contribute fewer hard photons per unit light, shaping warmth and structure, while sharper sources carve the biggest ionized cavities. Survey design matters for the verdict, so the community mixes blank fields for honest baselines with cluster fields for reach, and the persistence of the same signatures in both styles argues against a stage trick. Completeness curves, selection injections, and false positive rehearsals keep the sample honest, so the survivors are not artifacts of taste, but graduates of a hard school with many examinations. Ground support from adaptive optics confirms that the profiles remain smooth when the telescope changes and the atmosphere is tamed, which strengthens the claim that we are seeing single giants rather than blends. Variability analysis finds the slow heartbeat expected from a volume-powered engine, a rhythm set by density and capture, rather than by the appetite swings of a small disk that gulps and chokes. The spectral energy distributions that combine all instruments prefer cool color temperatures with high total output, a pairing that ordinary compact stars cannot sustain without thick dust, which the data do not support. Number counts sit in a reasonable lane where rare does not mean implausible and frequent does not mean absurd, a fit between theory and survey that leaves room for this population to matter without overrunning the sky. Inflow dynamics take on a new grace under gentle heating, since gas settles rather than riots, letting a star grow without breaking its own symmetry, and the light that escapes carries that symmetry as a smooth profile. If some of these giants end in direct collapse, early black holes begin life with a head start that eases the tempo needed to light the brightest sources by the first billion years, making the timeline tight but no longer desperate. If instead a fraction ignite fusion late, we gain a short bridge to familiar stellar behavior that may leave faint signatures in future deeper spectra, a gentle coda to a long inflation. Environmental checks suggest these sources prefer the hearts of young halos, where the invisible mass is densest, which fits the need for supply during the inflated phase, and maps onto where early structure most efficiently collects. Weak lensing shear maps in the neighbourhoods look ordinary rather than extreme, so the geometry does not need extraordinary alignment to explain what we see, another quiet point in favour of authenticity. Radio silence persists even as integration times deepen, which keeps the compact engine hypothesis on a short leash for the cleanest cases and gives the extended surface room to own the scene. Mid-infrared restraint holds when the exposure grows, suggesting we're not missing a dust chorus that only appears with deeper listening, a persistence that helps lock the interpretation. The near-infrared continuum shows the same soft slope after independent pipelines, which means the signal is not a processing ghost, but a durable shape that travels from team to team without changing its face. We have learned to fear easy miracles, so every claim is fitted with a shield of calibration tests, roll angle swaps, background strategies, and aperture tweaks, and the shield has held while the candidates stood in the open. The simplest summary is that multiple independent signatures point to extended, cool, luminous bodies at extreme distance, and the most natural engine for that combination is internal heating sourced by invisible matter interactions. The simplest caution is that a subset may still be blends or compact engines in disguise, so continued spectroscopy and shape checks will decide which stories hold and which dissolve. Either outcome refines the map because a verified class anchors models of early growth, while a false alarm sharpens our tools, and prevents future confusion across the same terrain. For the viewer, the promise is clarity delivered at the pace of reality, not a rush to name, but a patient assembly of evidence across instruments, fields, and seasons until the picture no longer tilts under its own weight. The story also restores humility to the timeline, since light that began with hidden fire may have prepared the ground for the first hot furnaces, proving that cosmic dawn was layered rather than single note. We can now say what would tip the balance fully: a handful of gold standard detections with tighter distances, cleaner profiles, deeper mid-infrared limits, and perhaps a whisper-thin recombination halo that fits a broad photosphere. We can also say what would break the case: strong dust signatures rising with deeper exposure, fast variability inconsistent with a swollen body, or lens models revised to extreme magnifications that shrink the true size. Until those doors are opened or closed, the most honest conclusion is a working interpretation held with firm yet gentle hands. That the James Webb Space Telescope has found the best evidence so far for stars powered by dark matter in the first billion years. This interpretation explains the uneasy brightness of the early sky, eases the path to heavy seeds, softens the tone of rionization, and leaves a legacy of methods that turn romance into measurement. It also gives us a lens to read future data with fewer blind spots, because extended cool brilliance is no longer a paradox but a signature to test for with care. As we close this segment, we keep the hook honest, promising the final step will not be thunder but agreement, a chorus of instruments saying the same quiet thing about lanterns that learn to shine on invisible fuel. If that chorus holds, the first stars traded urgency for patience and still lit the path forward, proving that absence can be turned into power, and that power can be read from the shape of a hill of light. If it does not, the lesson is still graceful, reminding us that the cosmos will always prefer the truth that survives repetition over the story that only dazzles once. So we finish this arc as we began, by letting the oldest photons speak, by letting careful tools listen, and by letting a measured verdict tell us whether the earliest beacons were swollen by darkness lit from within,